Welcome back. So this is the second part of the series of presentations on rotational motion, and I'm going to continue the rotational motion with the introduction of angular equations of motion. Alright. So let's see what are the angular equations of motion. You may already know by now what are the equations of motion for a straight line. So I will introduce what are the equations for a angular motion, and then it will certainly be used for the rotational motion as well. Alright. So I'll draw the diagram again. So let me review this. Explaining what are the equations of motion. I'll take this point as the origin, and this is the radius of the circle. Alright, and then I'll put this one here. I'll put some object here. Right, and then I'll say the displacement of the position of this particle is theta I, and I will displace it over, I will say this at time t equals 0 by the initial position, theta I, initial position at time t equals 0, and I will displace this object by some angle with this position. Now, I discussed this in angular displacement, but we have to understand it again, or if you are well versed in that, you can memorize it for this part of this presentation, but it will certainly be helpful if I go from the start. T equals T, I call this angle, this in the counterclockwise direction, and this is also in the counterclockwise direction. Remember, angle is always measured in the counterclockwise direction, not in the clockwise direction. Alright, so I'll call this displacement as theta, and theta equals theta f minus theta I. Alright, but for the following derivations I will not use the value for theta f for the value for theta I. I will only use theta. I will only use this. Right? So, if the angular velocity of this object at time t equals 0 is omega, as omega naught or omega I. Omega, yeah, it's omega is easy for you because I said this has theta, so omega is useful for you and it's easy for you. And since this is theta f, I'll call it the velocity at this point as theta f. And this is a motion I describe as a motion in acceleration. So this is an acceleration. So theta I is not equal to theta f. You can do the same acceleration, you can put the same velocity so that the acceleration is 0, and then you can say omega I equals omega f, it's going through a constant angular acceleration. But to derive the equations of motion, I will consider a body moving in a circle, which is in angular motion, in some acceleration. I defined acceleration in angular motion as alpha. So alpha should be equal to what? Say, and omega net should be equal to what? So that's the question. If you can answer those questions, we can easily derive the angular equations of motion. You know that in translational motion, as I said before, I always take the analogy or the relationship between translational motion and rotational motion for the first part of this first few videos of this lecture, series of lectures, because it's always easy for you to understand the concepts in rotational motion. So I'll take an object here, I'll call this simple mass here. So this is as time t equals 0, and this is time t equals t. Yes, I think I'll say that the object has been displaced by a distance d within the time t, and the velocity of the object at time t equals 0 is vi, this is the initial velocity, and the velocity of the object at time t is equal to vf, which is the time velocity. So you know from the translational motion that the distance is equal to delta v by t. Right? Distance is equal to delta v by t. So delta v is equal to vf minus vi by t. Oops, sorry. No, this is acceleration, right? I think in the first one also. Right, it's acceleration, right? I didn't mean this. Acceleration is equal to vf minus vi by t. So you know from this, vf equals vi plus at. Right? This one. So, if this is an acceleration motion, what's the displacement of the object? Displacement of the object, you can take it from the, say now this has a constant acceleration here, and draw a VT graph. Right? Solution here, I will say this one has Vi and this has Vf, and this time t. So the displacement of the object is the area under this area between this line and the time axis. So this is a trapezium. So this part of the lecture is not relevant to the angular motion, but I am deriving. If you are not followed my series of lectures on straight line motion, so I am deriving it and I will use it for angular motion. Okay, so the area of this trapezium, I call it D, is equal to half times addition of the two adjacent sides. So this is Vi, sorry, two opposite sides, Vi, and this is Vf times the altitude, this t. Right? So this is equal to D equals Vi times t plus Vf times t by 2. Right? Now you know that Vf equals Vi plus At, so D is equal to Vit plus Vft is equal to Vi plus At times t by 2. So here is Vit, here is Vit, and here is Vit. So this 2 Vit divided by 2, that's equal to again Vit plus half times AT squared is equal to, so this the normal equation we use as S equals ut plus half AT squared. And you can similarly you can derive V squared equals U squared plus 2AS and S equals the average of the two velocities times T. Right? So those are the translational equations of motion, and now I'm going to derive the angular equations of motion in a similar way. So first of all, I will write the translation equations of motion first. So V equals U plus AT, S equals UT plus half AT square, V squared equals U squared plus 2AS, and S equals U plus V by 2 all these times T. Right? So these are the four linear equations of motion, and now we have to derive angular equations of motion. So I call this object here as if this object at time t it has a velocity of omega I, and at time equals 0 it has a angular velocity of omega I, and at time t it has an angular velocity of omega f, and its angular displacement is theta. So in a similar way, I can just substitute the values. I will take this equation, V equals U plus AT. From the first part of this lecture, I always made a relationship between the translational motion and the angular motion. So I should be able to make a relationship between the translational motion and rotational motion in the course of the angular equations of motion. So I'll substitute the angular quantities in place of the translational quantities here. Omega, which is also called Vf, equals Vi plus A times T. So the term which is analogous to Vf in translational motion is omega f, and the term that is analogous to Vi is omega I, plus the term that is analogous to A in rotational motion is alpha times T. So for simplicity like this, I write it as omega equals, and take this one as omega naught plus alpha. Similarly, I take this out, S equals ut plus half times AT squared, right? I substitute the value, substitute the analogous term for S in rotational motions, which is theta. Theta is this angular, this one, angular displacement from theta I to theta F. We can time T, and this is called theta, right? So theta is equal to U is omega naught T plus half times the term that is analogous to A is alpha T squared. And I'll take this equation, V squared equals U squared plus 2AS, and term that is analogous to relationship to this one is omega f, but I will write it straight as omega, as in here, and that squared equals U is omega I, and I will straightly write omega naught equals this one, omega naught squared plus 2 times the term that is analogous to A, which is the acceleration in translational motion, is alpha in rotational motion and the term that is in velocity is t. So omega squared equals omega naught squared plus 2 times alpha times theta. Right? So the next equation and the final equation is c equals u plus v by 2 times t. So we can write theta equals omega naught plus omega by 2 times t. So those are the 4 equations of motion, and in the next lecture I will meet you with a new concept, the right hand rule, the moment of inertia, and the other quantities like rotational kinetic energy, and some exercises related to those. See you then.